You know that static hiss you get on an old radio? Well, it turns out there's a kind of cosmic version of that, a universal hiss. And it's not just an annoyance. It might be the single biggest thing holding back the entire future of computing. Today, we're going to break down what's really putting the brakes on quantum computers.
So let me just ask you, what do you think it is? What's the #1 roadblock to building a truly powerful quantum computer? Is it making the qubit stable? Is it the unbelievably complex algorithms? Well, the real answer is actually something much more fundamental.
Yeah, it's not what you think. The answer is way more, well, mundane, but at the same time so much more profound. It's a problem that plagues every single electrical component in the universe, a challenge that's honestly as much about plumbing as it is about physics.
And that unwanted guest is heat. I know, it sounds almost too simple, right? But in the ultra-sensitive quantum world, heat isn't just a nuisance. Oh no, it's a system-killing saboteur. And the craziest part, the way we currently build these machines basically invites it right through the front door.
Okay, so here's the core of the issue. To do anything really useful, we need to be able to control thousands, maybe even millions of qubits. You know, the basic building blocks. But right now, the standard way to do it is to use one big, thick, coaxial cable for every single qubit. The math here is just brutal. It means you hit a hard wall at just a few hundred qubits. And why? Because the very cables we're using for control are actively destroying the whole system.
And this image, wow, it just lays out the dilemma perfectly. See, up here, you've got the regular room temperature electronics, the stuff that's generating all the control signals. It's hot. But way down here, where the qubits actually live, it has to be kept near absolute zero, unimaginably cold. The bridge connecting the hot world to the cold world, yeah, that's the problem. Let's just compare for a second. Those coaxial cables are a total nightmare. They have a huge thermal load, which means they basically act like giant metal straws, just sucking heat from the warm room and dumping it right into that delicate cryogenic freezer. They're bulky, they're complex, and they get insanely expensive as you scale up. What we really need, the ideal link, is the complete opposite. Something compact, simple, cheap, and most importantly, it would carry almost no heat at all.
So you see, this whole heat issue isn't just about sloppy insulation or something. It's connected to a fundamental property of matter itself. And this is where we get back to that universal hiss. It's a noise that is literally baked into the fabric of physics.
It's called thermal noise, or if you want to get technical, Johnson-Nyquist noise. To put it simply, it's the random electrical noise that gets generated just by electrons jiggling around inside any wire. It doesn't matter if there's a voltage or not. If something has a temperature above absolute zero, it's got this noise. It's basically the sound of heat itself.
And this isn't some new discovery we just stumbled upon. Albert Einstein himself hinted at this way back in 1906. Then, fast forward to the 1920s at Bell Labs, a researcher named John B. Johnson actually experimentally measured this mysterious static. And right after, his colleague Harry Nyquist came up with the brilliant theory explaining exactly where it came from, linking it directly to the fundamental laws of thermodynamics.
So here's the crucial point, and this quote from a surprisingly deep debate on a Wikipedia talk page just nails it. The noise isn't a flaw in the component, like a resistor. It's a fundamental property of the electrons themselves, jiggling around because of heat. You can't just engineer it away. You have to find a completely different way to get around it.
So, if electrons carrying heat are the problem, how do you solve it? Well, you find a new messenger. And that brings us to a really elegant potential solution, using light.
This is the simple, elegant question that researchers are asking right now. What if we could communicate with the qubits, send them all the complex instructions they need, but without opening that thermal floodgate and letting all that destructive heat in? And this right here, this is the plan. It's called a photonic link, and it is an incredibly clever workaround. Okay, so follow me on this. Step 1. At room temperature, you take your qubit control signals and you modulate them onto a laser beam. Step 2, you send those light pulses down fiber optic cables, which are fantastic insulators that carry almost no heat. Step 3, deep inside the fridge, at the super cold 4 Kelvin stage, you have a tiny detector that picks up the light. And finally, step 4, you convert that light signal back into the microwave signals the qubits need to operate. You get all the information with none of the heat. It's just elegant.
So what happens if we crack this? The implications are just enormous. This isn't just some small incremental improvement. We're talking about fundamentally changing the architecture, the blueprint of a quantum computer to finally allow for massive, massive scaling.
Because this approach doesn't just get us past that few hundred qubit barrier. No way. The research suggests it could let us blow right past it and start controlling thousands of qubits, and maybe many more after that, all through just a handful of optical fibers.
So, the big takeaway here is that solving this plumbing problem, that physical connection between our normal hot world and the freezing cold quantum world, that's the key. That could be what finally unlocks the door to the large-scale, fault-tolerant quantum computers that scientists have been dreaming of for decades.
And it leaves us with this fascinating thought. For decades, we've known that heat and the universal noise it creates is the great enemy of the quantum realm. But maybe, just maybe, its perfect counter, pure, clean, cold light, is the savior we've been looking for all along.